Thanks, Sami. Thank you, everyone. Yes, it will be a lightning talk. There'll be a lot to pack in for this session. So I just please ask if we save the questions to the end or to after, and happy to field them through the platform. And as Sami said, I'm going to be walking you through using graph embeddings. So a few of the graph algorithms that were available in Neo4j for my research topic, which was tracing ransomware payments throughout the Bitcoin network. So I hope everyone can see the slides okay. So where did we begin? So a little bit of introductions. Yeah, I only started using Neo4j graphs back in 2018, essentially when I started my journey on my PhD, which is just completed. Thanks, Sami. And the focus, as I said, was on tracing suspicious Bitcoin payments. This was in general at first, and then it sort of narrowed down into actual ransomware payments throughout the Bitcoin ecosystem and the transaction graphs that they formulate. And then, in order to get a bit more of a deeper understanding of the graph and the context of the graph, I started exploring the Graph Data Science library that Neo4j offers. So what did I want to do? Well, the intention of the research was looking at ways of disrupting the ransomware payment networks. As you can see there on the right-hand side, there's quite a dense and sparse graph of let's say a transaction graph of a ransomware attacker transferring their funds throughout the Bitcoin ecosystem. And I wanted to know about these Bitcoin transactions, how they formed their graph, what patterns they were making. And I needed a visualization tool to help me do that. And Neo4j was something that helped enable that and allowed me to understand the behaviors a bit more better when it came to ransomware payments. But adding to that, just looking at the graphs, analyzing them, as I mentioned, they're quite dense and sparse. I needed to formulate some contextual information out of that. And in order to understand the relative riskiness of such payments with respect to ransomware seed addresses, I needed to look for that contextual information. And the ultimate goal was to try and predict clusters that certain nodes, certain addresses, or certain transactions would belong to. And by doing that, I looked into the graph embedding algorithms available from Neo4j. So where do I start, right? Well, if anyone's familiar with the cryptocurrency ecosystem, you'll know that there's a lot of data, right? And the data that it forms is, in natural essence, it's a graph. And modeling this, I was helped greatly through the use of Neo4j, right? It allowed me to take two sides of my problem, which was, how victims are paying in to the collection address that an attacker would control, and then how the attacker then moves those funds beyond the collection of those ransom payments. So I started with a bit of a Python script hack and plugged into a Bitcoin API just to get the data, and then I loaded that into the Neo4j system. Okay, so two graphs essentially, a cache in and a cache out. But, what did that mean? And you can see there in the top right-hand corner, what is the signal within all this data? The different levels away, so the depth of the graph, the density of the graph, and I needed a way to simplify that model. And as I mentioned before, Neo4j sort of enabled me to do that. It enabled me to embed properties and use those as an enriching feature of my graphs, and essentially, what I could use down the line in my, let's say, machine learning pipeline to further understand the graphs. And this is where the embeddings really proved a bit of a game changer for the research I was doing. There were two embedding algorithms that I looked at. Okay, the first one was the deep walk algorithm. And the second one was the graph sage. I'll first run through the deep walk algorithm. So a little bit of background on that. It was was made famous in a 2014 paper by Perozzi et al. And they used it against the Zachary's Karate Club graph, which is a very famous sort of data set when using to test embedding algorithms. If anyone's interested, I highly recommend reading that paper to get a deeper understanding of the embedding concept that Deep Walk was looking at. Okay, essentially Deep Walk allowed me to learn structural representations of the graph's nodes, and I could capture the similarity in a whole neighborhood. So one of these graphs, one of the cache out graphs, I particularly focused on, and I was allowed to embed those learnings into the individual nodes within the community of the graph that I was looking at. On the right-hand side, there are a few high-level steps that I went through, and I'd like to share those steps along with some of the code that I used as well. And this is shared afterwards, so please feel free to access the GitHub repo and try and play around with some of this code as well. Okay, so if I step through this flowchart here, so as I said before, so I needed to read in the data into Neo4j. So what did that mean? That means using let's say the APAC load to read in my JSON file. So when I did my data collection, I had a big JSON file which basically formulated the graph that I was interested in. Okay, and with this loading function, I was able to basically set up my data model. So using my addresses as the nodes, the payment transactions as links between those nodes, and then henceforth building the chain of transactions from there. Okay. What was also interesting for me is what I call the depth property. This was also built out of the Python extraction code, and what it allowed me to do was tag each hop, let's say, within the network away from the main seed or collector address that the ransomware attacker was using. So I was interested in, let's say, what happens 4 hops away from that particular address, and then how the transaction graph develops from there. So I could look at any point, any sort of hop away from that address to see what's happening at that level or that depth. This was a very interesting feature for me to use in downstream feature engineering. Some of the other graph data science functions that I was able to use as well were PageRank and community detection. So how did I use them within, hope it's not too small, within the Cypher code and within the graph data science library in Neo4j? Basically, you could call the community detection algorithm that's available within Neo4j, and that would stream out and provide a metric with respect to each of your nodes or transactions within your graph. Okay, PageRank was also used in a similar fashion. Then, with my graph, let's say, set up with the appropriate properties that I wanted to use that for my use case, I was able to then execute the deep walk algorithm and then write the embeddings as vectors to those nodes. So quite a simple piece of code there that was allowed to basically run across my graph with the appropriate hyperparameters. And if you do look into the academic paper, there is some explanation around what might be the optimal set of hyperparameters to use with respect to the graph that you'd like to apply this algorithm to. Okay, but these embeddings essentially allowed me now to form some sort of contextual understanding, and the deep walk algorithm really does observe each node, right? It takes a random walk from your starting point and then builds this data corpus and reference library, essentially, that you can use to use these embeddings as effectively features for any sort of further machine learning as well. Okay, so that last step there, I had the export to Python to perform some principal components analysis and a k-means clustering. And this was important too. I mean, I used just a Jupyter notebook in order to reduce the embedding dimension down to something a little bit more digestible, and something that would be able to be analyzed in a 2D space rather than the whole vector space that Deep Walk uses. Okay. And essentially, that's how I exported it. It's really quite simple within the cipher in order to get your data set and then really connect that to Python to do a bit more of data science analysis. So that was the Deep Walk approach, right? The next algorithm that I tried, oh, sorry, before I get to that, actually, what were some of the outcomes of that, actually, which is good to mention. So Deep Walk itself is a transductive algorithm, right? And as I said before, it steps across every node and every aspect of your graph that you would like to perform embeddings on. It operates in more of an unsupervised manner, okay? So versus your standard sort of testing, training, and validation machine learning pipeline. But this is okay. I needed something to basically get a perspective of what might be important and contextually relevant within my graph in a quick and easy fashion, right? And the purpose, as I said at the start, was really to try and find some risk in the nodes within a ransomware payment network. So I was able to use these embeddings that were derived from Deep Walk, push them through the principal components analysis and k-means clustering, but also then use those embeddings, those reduced embeddings in a cosine similarity function that really looked at the risk relative to this ransomware seed address, okay? So stepping out of Neo4j into my Python notebook, I was able to start ranking the riskiness of each of these nodes within my ransomware payment network. But saying that, you know, the Deep Walk algorithm applied to my graph in Neo4j, it's actually not available in the Graph Data Science library. It was actually it's actually in a GitHub, which I have a link to, and you install that separately within your setup for your Neo4j database. And it produced a few, you know, questionable outcomes, I guess. You know, why a higher community risk does not correlate to a higher concentration of risky nodes? Because you can look at them individually, but you can also look at them collectively. Because my objective was to try and disrupt the whole network. Okay, so where's that concentration of risky nodes? But it's not in a very risky community. And if you remember, I used the community detection and the page rank as some indicators of that. Okay, I didn't test any performance or scalability of the algorithm as well, so that's something to take into consideration as a watch point. Conscious of time here, so I'll push through to the usage of the graph sage algorithm. So the graph sage algorithm is actually available in beta within the latest version of the Graph Data Science library. So a lot easier to integrate into your Neo4j database. And the graph sage algorithm differs from the Deep Walk algorithm as it's more an inductive algorithm, right? So in essence, Hamilton et al. Back in 2017 established this for learning on large graphs, okay? So I was able to generalize a function that would try and represent your graph and the node feature information within the neighborhood proximity to generate the node embeddings. I encourage you to take a look at that paper as well. It's very informative in how the algorithm executes and how it's actually implemented within Neo4j. There's a lot of good information in the developer docs. Okay, so again, I read in the data. So the first two steps are fairly similar. Yes.
We have nearly reached the time. Maybe.
Oh, sorry. Okay, I'll really speed through this, right, and just give you some outcomes of what's happened within the output of the graph sage. Okay. Again, I stepped through this. There was a few different steps in the process regarding my risk rating element. I actually did the risk rating within the cipher code. All of this can be shared and accessed through the GitHub repository as well. I used the concept of the graph catalog, which is a very powerful component of Neo4j, and it allows you to use this multiple times within your analytical workflow. Okay, so that was another benefit of using graph sage. And it was more executed in a supervised fashion, right? So you'd have your traditional testing, training, testing, and validation data sets. And what it revealed is some different types of graphs within my overall graph. And it allowed me to do a lot more, let's say, specific feature engineering, okay? Which helped me, in essence, achieve my objective of trying to predict where a node, an address or a transaction may belong as a part of a cluster. Okay, so I broke down these 3 graphs into small transaction clusters, seed transaction clusters, and large transaction clusters. So some key takeaways, and of course, please feel free to connect with me on LinkedIn and ask me questions after this presentation. But looking at the graph embedding frameworks for Neo4j, they really give you the opportunity to provide rich context for complex graph understanding, which is what I needed for my research, okay? You can build feature stores and enrich your graph with knowledge, okay? This is another great benefit of using the Neo4j platform and the Graph Data Science library. Deepwalk, as I said, is a transductive algorithm. GraphSage is an inductive algorithm. Encourage you to explore the differences between those two. The Neo4j Graph Catalog, a really powerful feature to help you manage multiple graph projections or multiple feature engineering within your analytical workflow. And of course, the Graph Data Science library from Neo4j is something that enabled me to successfully complete my research degree. Okay, I thank you for your time, and apologies for rushing through that a bit at the end.